Thank you. Thank you for the opportunity to tell you about some work I'm very excited about that I'm doing as part of my PhD at the University of Waterloo. My advisor there is Oliver Pachenik. I'm particularly excited to talk about swinger fibers because we talked so much about them today. The clicker is not clicking. Sorry, that's all right. There we go. So our story starts. I'm going to go back a little further. Whoop.
Down is forward.
Down is forward, of course. So our story starts a little further back than what Martha told us earlier. Back even in the 50s, we were thinking about this thing called the nilpotent cone. It's a set of nilpotent elements in a semi-simple Lie algebra. It turns out it has this cone point, it's singular, so you resolve the singularities, and that's what Springer did back in 1969. The fibers of that resolution is what we're studying today. A couple of differences you might notice from Martha's conventions. I'm always going to be talking about a nilpotent matrix, and I've got this off by one error here, or not so much an error, but when I hit a vector space with a nilpotent matrix, I'm definitely losing dimension. So I'm never going to be exactly equal to the space I started with, so VI can be replaced by VI minus 1 from what Martha. Okay, so these fibers, Martha was very generous to tell us some nice reasons you might care about Springer fibers. This fiber doesn't carry an action of the symmetry group, but when I take homology, I suddenly pick one up. I find that surprising. And the top graded piece is the spec module associated to the partition I would want, which I also find surprising. And also this homology, when I take graded Frobenius characteristic, I get symmetric functions that you might care about for other reasons called Hall-Littlewood polynomials. Again, I find this surprising. But okay, despite all these nice applications, we have like one overarching geometric theorem, and that these fibers are equidimensional, connected, and they have components indexed by standard Young tableau. If we want to say anything more, we sort of have to specialize, even though we've been thinking about these for 50 years. So back in 1969, here's the resolution. Very quickly, we had this one overarching theorem. And it took a little while to understand the very special case of the two row Springer fibers. These are very special. All of these components are smooth. Very nice things happen. We heard Mackenzie saying things about the two row case just a minute ago. But the upshot of this case is that I don't want to think about this tableau indexing set that Schwalbenstein gave us. I want to actually think about non-crossing matchings. And these non-crossing matchings tell me geometric things, like how to read off the components, and also how to think about the intersections of the components. Mackenzie drew some nice pictures in her talk. Now, if you were here last week, you might know non-crossing matchings by another name, that name being SL2 web basis. And I don't have time to do this justice, but these give us a diagrammatic calculus for some complicated vector space associated to representation theory. Here's a Pluker relation. That should hopefully jog your memory from last week. This was generalized to SL3 by Kuperberg in 1996, and it's sort of open in general to do this for high rank SLR. There are lots of reasons you might care about webs outside of Springer fibers. Here are some buzzwords that you can look up later if you're so interested. There's some relation to knot theory and Kovanov homology. There's some cyclic sieving. There's applications to cluster algebras and more. And like I mentioned a second ago, and like we heard from Jessica, we have an SL4 web basis, but not an SL5 web basis. And the upshot from the two row case, and maybe the hopes and dreams we might have, is that we can use what webs we do know, what web bases we do know, to get a better understanding of the components of Springer fibers. So other work more recently was about the two column case for Springer fibers. And people worked very hard, Professor Melnikov and Slakhaskov, they worked very hard to say some things about the two column Springer fibers from the tableau. Let me show you what I mean. Let me tell you their results. So if I take a two column tableau, we can characterize which components are smooth, and I have to look at the ascents in my tableau. The entries in the first column, whose successors in the second. These are ascents in the column lattice work. And if I have very few ascents, I'm definitely smooth. And if I have too many ascents, I'm definitely singular. The other condition says I can split up my tableau into two. And the theorem is even better than that. They say when I'm smooth, they can describe the bundle structure. They can say that it's an iterated fiber bundle with base. flaggy things and Grassmannian things and projective spaces where you have to like look up into a table what these values are, and that is unsatisfying to me. And it's unsatisfying to you too, because here are two tableaux, and it's probably not obvious to anybody. Well, one thing is obvious, that these tableaux are very similar, but it's not obvious that the one on the left is singular and the one on the right is smooth. And it's probably also not obvious, unless you have a very good memory, that the bundle structure for the one on the right is that. I don't know where to see a 5 in that tableau. So let me reinterpret this using a web basis. This is the web basis of Chris Fraser, and I'm drawing my pictures in the hourglass conventions we learned last week from Jessica. And the main theorem is that this example is going to be generic. Generic insofar as the singular one is the one that's sort of worse. And by worse, I mean more complicated. By more complicated, I mean having a cycle. Cycles are definitely more complicated than trees. So these cycles are telling me that I have a singular component, and the lack of a cycle tells me that I have a smooth component. And if I throw the bundle structure up there as well, you can hopefully guess about how I'm going to read this off from the web, because there's exactly one thing about this web that is 5, and it's the size of this first claw. There's exactly one thing about this web that is 4, and it's the size of the second claw. I've got a size 3 claw that's telling me my Grassmannians in 3 space, and I've got a 2, and that's actually, I look at that edge there. I've got 3 copies of projector space, which I also read off from the last claw, and the dimensions of those projector spaces are predictable. So that's the main theorem. The smooth components of 2 column string fibers exactly correspond to the acyclic webs in this 2-column web basis. The geometry is exactly described by these claw sizes. A nice consequence of this is when I compute the Poincare polynomial of my smooth components, these Poincare polynomials are equal if and only if my webs are a rotation or reflection away from one another. And one last little perk of this, we're at a combinatorics conference, I can count these smooth components really well, really easily, much easier than from the tableau description. And I know that because there was a paper with an error in their count of the tableau from the tableau description. So we corrected that, and there's this nice, there are K sort of in a degenerate case that I didn't put on the board, and there are 2 K choose 3 from the ones that sort of look like the ones I've common. I hope this has sort of piqued your interest in the webs and correspondence to Springer fiber components. There's more work that I didn't have time to talk about today that's sort of in progress that I hope to tell you at a later date. Thank you.
We have a question for Mike? Yeah, we're not dividing the 2 components.
Yeah, so there is, I learned after this that there is there are things known about the intersections of 2 components in the 2-column case using link diagrams, sort of the non-crossing matchings again. I'm not sure what that looks like with webs. It's not obvious to me.
The webs can see singularities, but maybe not intersections.
Oh, I don't want that to be the truth. I hope there's a way to see it on the web, but we haven't figured that out yet.
Okay, let's say further questions for dinner. Thanks, Mike.